A bar of mass 1 kg and length 0.2 meters lying on a horizontal frictionless surface. An object, a small mass of 0.1 kg is moving on the same horizontal surface with a speed 5 meter per second on a path perpendicular to the bar. Hits the bar at a distance L by 2 from the pivoted end, returns back on the same path. This is a question of a classical mechanics in advanced 2023. Now see dear, this question can be easily approached with the help of a free body diagram, or let's say a diagram which depicts the entire situation. You can refer back to this question's data later on by moving back on the video. Now see this. The rod which is lying on the surface is, let's say, positioned like this. Let's say this is the rod. Now this rod of mass m equal to 1 kg and length L is pivoted at this point of O. It is pivoted at this point and it can rotate about this axis, and the length L is 0.2 meters. Let's say this is the position on the rod at which the distance is L by 2 from the pivoted end, and the object is approaching the rod in this direction. This is the small mass given as equal to 0.1 kg. 0.1 kg mass moving with, let's say, an initial velocity u. The velocity is given in the question, is moving with a speed of 5 meter per second, and it moves perpendicularly towards this particular rod and hits it perpendicularly, and then what happens? This is before collision, and after collision what happens? The rod begins to rotate with an angular velocity omega, and what happens to the object? The object returns back on the same path with a speed v. Both omega and v has to be found in this situation. Any external torque is involved in this situation. Net external torque being 0, this net external torque being 0, then dl by dt is 0. That means angular momentum L, as the L naught, let's say L about O, the angular momentum is conserved. If angular momentum is conserved in this situation, then are we having any initial angular momentum provided to the system? Oh yes, this object with a mass m, with a speed u, and with a perpendicular arm length of L by 2 hits the object, provides an angular momentum before collision, pre-collision, and therefore angular momentum about point O initial is equal to mass m, speed u, and a perpendicular arm length of L by 2 enters the entire system. Then after collision what happens? This angular momentum should be conserved. So the angular momentum of the rod about this point O is I naught into omega. This is the angular momentum in the positive direction. Let's say it is conserved. And it is allotted to the rod. Rod rotates with the angular momentum I naught omega. And what happens to the object? It returns back with a negative v. I mean v in the opposite direction. That means the mass with this particular mass returns back with a velocity v with a perpendicular arm length of L by 2 from the axis of rotation, and therefore this is the first equation which we will use in solving. In this, the entire values, if we put, the moment of inertia of the rod or the bar about this point O should be equal to ml square by 3. So if this is equal to ml square by 3, the value should be 1 into L is how much? This L is equal to 0.2 meters, I think, as is given in the question. Oh yes, is equal to 1/5 of a meter. So this is 1 by 25 into 3, 1 by 75. So this is 1 by 75. I naught value is 1 by 75. Small m is 1 by 10. U is a 5 and L, the length of the rod, is 0.2, that is 1 by 5, that means this is another 1 by 10, is equal to I naught 1 by 75 into omega minus small mass is 1 by 10 into V is unknown into L by 2 is 0.1, therefore another 1 by 10. So therefore this is effective. 5 goes and brings 2, so this is 1 by 20 is equal to omega by 75 minus V by 100. Let's multiply by 100 all throughout, make it 5, and 100 by 75 means 4 by 3 of an omega minus V. Let's keep it as it is. Let this be equation number 1 in the solving. Now next is, as this particular object hits and gets back with an elastic collision, as is said in the question, this is an elastic collision. Now if this is an elastic collision, then kinetic energy should also be conserved. Now let's see the kinetic energy situation. The kinetic energy that is initially available is half mu square is what this object comes with. Then this energy is allotted to the rod to rotate, and that makes it half I naught omega square, kinetic energy of rotational motion of the rod, plus the kinetic energy retained by the object to get back in the reverse direction. This is the kinetic energy conservation equation. Let's put things into this. Let's cut off half. Now small m, that is the object, is 1 by 10 and u square is a 25. I naught is equal to 1 by 75, hopefully that we have calculated. Oh yes, 1 by 75 into omega square plus, of course, small m is again 1 by 10 and a v square. Now let's multiply by, let's say 10 all throughout. So 25 is equal to 10 by 75. 5 into 2 and 5, 15. Omega square plus v square. I multiplied by 10 all throughout. So that makes it 25 and v square. This side 10 by 75, 5 2 is 515. So this is the second equation that we got from this situation. In an elastic collision, the momentum is conserved as well as the kinetic energy is also conserved. Now we solve these two equations to get v and omega values. Let's replace v. V is equal to 4. If we place v is equal to 4 by 3 omega minus 5. 4 by 3 omega minus 5 into this. What we get is 25 is equal to 2 by 15 into omega square plus v square. V square would give us 16 by 9 omega square plus 25 minus 40 by 3. 20 into 240 by 3 omega. This is what we will get. Now see, 25 can be easily cancelled off from both sides. And about omega square, what exactly do we have is a 2 by 15 plus 16 by 9. Quite odd numbers here, but we can work. This is omega square. And 40 by 3 omega. 40 by 3 into omega. This equation can have the solution as omega equal to 0, but since omega is not equal to 0, let's say since omega is not equal to 0, that means 40 by 3 omega, omega cancelled, is equal to 2 by 15 plus 16 by 9 into omega. So therefore, your omega value is going to be 40 by 3 into 15 into 9 by 18 plus 15 into 16. 15 into 16. So that makes it 16 into 10, 160 into 80, 240. 240 and like this. So omega is roughly 40 by, this 3 can cancel, make it 3, and that means this can be 600 into 3, that is 1800. If I'm not wrong, 600 into 3, 1800, or 45 into 4, 45, 91, 1800 by 258. 258, I'm so sorry, 258. Approximately how much? Approximately, I think you see, approximately this is going to be, it's like 258 into 2, 500, 500, 1000, 1006, 7 times This is going to be roughly close to 7 times. Let's try. 258 into 7. 7 8 is 56, carry 5, 35, 40, carry 4, 18066. I'm very close to 7, very close to 7 as an integer. And the answer in the book says this is 6.97 radians per second. This is omega. Now let's say omega is 7. Then if omega is 7, how much is V? So if omega is 7, that brings me V is equal to 4 by 3 into 7 minus 5. So 28 by 3 minus 5. So V is equal to 28 minus 15, that is 13 by 3, very close to 4 meters per second. This is the second answer. Now see, this is the way we solve a very classical mechanics question about collision, about momentum, about rotation, and stay focused, stay revised. We are coming more on physics. Thank you for your patience.